Welcome to Chai and Why. With me today is Professor Pankaj Joshi from TIFR. He's an astrophysicist who works in the area of gravitation and cosmology. So today we are going to learn about the life and death of stars, and in particular this very exciting thing called black holes. So Pankaj, what is a black hole and why is it so exciting?
Well, Arnab, you see, when the stars are very, very massive, then they can't settle when they exist. They are inside nuclear fuel. They must collapse and shrink endlessly. And that is the exciting story which, brings in the black holes and fireballs into the picture. Well, come to the talk and we'll talk great details about that.
Okay, should be exciting. Thank you.
This is one of the greatest mysteries of the universe, which is the life and death of massive stars. You see, stars come in all variety and all denominations. Sun, as you know, is just one such star which is nearest to us. But then the other nearest, object which is like Sun is about 4 light years away. So, how isolated we are in the universe. And still, in our galaxy itself, as we will go and see, there are some 400 to 500 billion of stars. This is in just one galaxy, and then there are, millions of galaxies. So, on one hand, the universe is so vast and so separated. On the other hand, there is a single star like Sun, is living its life, burning its nuclear fuel. So, I will try to tell you something about the latest happenings in this arena in recent years. I will skip through some of the slides, but not too far ago in our own sort of history of what we know, we had some kind of an idea of a celestial sphere. Something out there spread on the sky, the stars located, from our distance from the sun when you look up there. But beyond that, if you try to look, somewhere there, it's all unknown. We see the night sky and you see, whatever is there on the night sky, and that is your, sphere of, stars. But beyond there, there were all sorts of speculations as to what is lying out there and so on. And then, the theories were there that we are all here, the humanity, and outside are the unknown forces sort of, governing and driving, the universe whichever way that they are doing. The important point is there are, major instruments, major telescopes which aid our, senses. And then we see the sky, you can see the, human being, the scientist sitting over there. That was the dimension in the early part of the previous century. And then today, as you know, we have, the telescope going in space. So you observe the universe out there using, this kind of major instruments. There are very important missions which have been, put out there. The SWIFT mission, for example, observes only the gamma ray bursts. Gamma ray bursts, what are they? Within tens of seconds, they give out energy as much as the whole of Sun's entire lifetime of 10 billion years. That much of energy coming within, a matter of few tens of seconds. Now that kind of a burst we are observing almost one per day today, out there somewhere in some direction, and this are supposed to be, the collapsing stars. When a massive star collapses, ends its life, it ends the whole thing in a catastrophic manner, and that is where, the story of black holes, begin. So to say, in fact, observations is not something new that we have started, just today. We are brand new 20th century, 21st century kids, guys, and and it's not like that. Way back, Chinese astronomers did observe appearance of a very bright star in our very Milky Way itself. That is our, you know the our Milky Way, that patch in the sky and so on. And suddenly there was a brightening. Suddenly there was a brightening of the entire night sky. You see, and it took almost 8 months to fade away from the sky. It sparkled like a star in the sky, but it was much brighter. It was very dominant thing. And today, what we call that thing as a supernova, with modern instruments that I was showing you, it looks something of this sort. But the important point that again I am making, I mean, there are many things. You see, many of these stars have amazing, just a few weeks ago we were talking to one Cambridge professor, and he mentioned to us that now today we have at least some 200 to 300 stars which do have in fact planetary systems. So, well, yeah, this is the telescope, named after, Professor Chandrasekhar. He is Subramaniam Chandrasekhar. Alright, so then you see the entire universe in this arena, and then you see major galaxies. This is one of them, and then as I was telling you, it's full of stars, and each one of these galaxies is having 400 to 500 billions of stars. These are the so many galaxies actually. I showed you one or two, and then that kind of a universe is supposed to have emerged out of a big bang. What I was telling you was that it is the stars which we need to understand. What is happening within the stars, if we try to understand that, then that tells you a lot on the universe. You must have read, only recently there was this Nobel Prize on accelerating universe. Now the key observation that went into that particular phenomenon is the exploding stars or the supernovae. There was a completely two different supernovae projects carried out. And you observe in one of these galaxies, one supernova, how it is, exploding, how it is, emitting its light, and based on that, they are dimmer than they should, appear to be, and that tells you, essentially that the universe is going away faster. But come back to the, topic of a star. A star is, like a balloon. You blow a balloon. How it works? This balloon has this rubber, membrane that is pressing inside, but then there is this air which is pushing outside, and that is how is the balance of the balloon. As soon as you release the air, the whole thing shrinks, right? Similarly, for a star, what is happening? Similarly, for a star, what is happening is there are two main forces. One is there is this internal, fusion process going on inside the star. The atoms are combining, mainly hydrogen. Hydrogen atoms are combining into helium, and that releases energy. Then the helium fuses into carbon. Carbon fuses, so higher elements, ultimately iron. In all this process, the energy is generated. So all that energy that you get from the sun is hydrogen fusing into helium, and that energy is being radiated out, and the gravity, sun is not like this, I am standing here on the earth and solid body and all that. Sun is like a huge hydrogen ball, but sun is being held together, how? By the force of gravity. There is an inside pressure created by the nuclear burning, and then there is this outside shrinking going on. And this is how the star survives. Now, I showed you the picture of Professor Chandrasekhar. He found out one day on his way, to England, and then working there in England, that a star like sun, after it burns its, internal fuel, it will shrink. It will shrink, and it will make what is called a white dwarf. What is white dwarf? It is, there is another kind of a pressure That particular pressure is it's called electron quantum pressure. I will not give you technical names, but you know it is a white dwarf about 1,000 kilometer in radius, but very heavy. One spoonful of that will weigh you know tons and tons. But then if the star is beyond a certain 1.4 solar mass limit, which is called the Chandrasekhar limit, then it cannot settle into a white dwarf. Then it is becoming what is called a neutron star. So all the supernovae that I was talking to you, what they do is outer layers are blown off of the star and a neutron star is left. So if a star is as massive as some 4 to 8, 10 solar masses, then its outer layers are gone and a very heavy 10 to 15 kilometers of neutron stars will be left you know at the center. And then you know when Zwicky in 1930s pointed this out, people said this guy is crazy. How can you have a star 15 kilometers, tens of kilometers in radius, made only of neutrons, all electrons are fusing you know into neutrons, it's only neutron star, what are you talking? But then you see all this story was, you see, Chandrasekhar's work and you know other works. Chandrasekhar himself you know shifted to something else actually, other area. So all this work was termed as some kind of absurdities in you know 30s and 40s and so on. But in 1960s, then when these missions came up, then we observed such fantastic you know high energy phenomena in the universe. My God, I mean you look there and so much of energy is being produced. You see, what do? How you produce energy? You do chemical reaction, you know on earth you make a whole of your chemistry. Then the most efficient another means is this, as I was telling you, breaking atoms, nuclear energy, on which you know so much is going on. India में reactors बनाएंगे नहीं बनाएंगे, क्या करेंगे, Fukushima में क्या हो गया. So all this, that is the you know all that we can do. Solar energy is so diffused. But then when you observed in the skies out there, then you observed what are called active galactic nuclei. Active galactic nuclei, that is our own galaxy. You know, I think I am trying to compress everything, so I am not going in logical order actually as per my you know this thing. But you observe the you know center of the galaxy, this particular object is so massive. It is called the galactic nuclei and it is so active, so much is happening there, so that it is called AGN, active galactic nuclei. So this is some 10 to the 6 to the 10 to the 8 solar masses kind of object. Now this kind of AGNs people observed. Then people observed in 60s quasars, you see. Then people observed radio galaxies. So when they observed all these things, then you see this idea of neutron stars and this idea of you know black holes and all these things became you know relevant. To tell you again very briefly, there are massive stars and there are low mass stars like sun. Sun will happily live, you see, 10 billion years. But then when the stars are as massive as about 10 times the mass of the sun, they live only few crores of years. Think of it. From 10 billion years to the lifespan coming down to just you know a few 10 to 20 millions of years. So massive, more massive the star, life is shorter. So the question of the final fate of you know such short-lived massive stars is of central importance in astronomy and astrophysics. I am driving home a very basic key point. In fact, I can't resist you know quoting Chandrasekhar himself, what he wrote you know in 1935, and he said that it must be taken as well established that the life history of a star of small mass must be essentially different from the life history of a star of large mass. Small mass, white dwarf, you know, it will terminate into that. But then this is what he told in 1935. A star of large mass cannot pass into the white dwarf stage, and one is left speculating on other possibilities. Way back in 1935, he told this, and then this is, you see, from the physics committee report of Washington DC. Once I say Washington DC, people are happy. So, this is, you see, the report came from them, that their academy. They say maximum mass limit for neutron stars. The exact limit depends on the equation of state, etc. But the point is, any stellar core with a mass exceeding the upper limit that undergoes gravitational collapse must collapse to indefinitely high central density. So what I am telling you is from 1935 to 1980s, hardly much progress. Chandrasekhar said we are left, speculating on other possibilities. This report says, you see, oh, kuch hota hai. Okay, so what I am trying to tell you is this is the excitement of the entire subject, and the observational connection is the very high mass stars. Einstein's theory is the theory to work on this thing, Einstein's theory of gravitation, and then to come, okay, let me skip through this technical details at the moment. Let me tell you the summary conclusion at the moment. Some models were worked out using Einstein's theory of gravity. You see, we can, as I was telling you, you can observe one thing at a time. We are, even though our mind is so great, we dream during night as well as day. Alright, but still, when you actually try to observe, you can see only one direction, one thing, small at a time, integrate over the years, and over a lifetime, small amount of knowledge you gather and leave it maybe for the next generations, and so on. But in Einstein's theory of gravity, mathematical theory of gravity, that is the theory to use to work out this mystery. ये जो मैंने जो अभी बताया आपको कि ये भाई क्या होता है, large mass stars, what will happen is a star which has lived millions of years will catastrophically collapse within matter of seconds. You see, that is nature. You think everything is nice, everything is going fine, everything is stable, life chal raha hai, and suddenly a catastrophe occurs. So same thing happens in the life of the stars, and then you see a gravitational collapse occurs. This is a picture of a star collapsing, the internal fuel gone, and catastrophically within the matter of seconds, just like some industry going boom with some, some catastrophe happening. Similarly, with the nuclear fuel gone, the balancing pressure going away, gravity shrinks the star. Gravity is the eternal force. So then what happens is Oppenheimer and Schneider, worked out this model, Robert Oppenheimer and I think Herbert Schneider. So they worked out this model in 1939, and then they predicted for the first time using Einstein's theory, mathematical equations. So ये क्या कर सकते हैं यार? Either you look at there or do experiments, or you observe, or you work out mathematically your conclusions. So this is the mathematical conclusion. Black hole was worked out. The thing that happens is the star is shrinking. If you throw light, eventually it becomes so small that nothing can escape from the star. The gravity becomes so powerful. In the heart of a black hole sits the most mysterious object. It's called the Spacetime Singularity. That is where the laws of quantum gravity become operational. Quantum gravity becomes operational at higher, still higher, highest energy scales. I will not quote numbers, some 10 to the 19 GeV and stuff like that. I think it is enough for the moment. If you have questions, we will go into that. But then there is the space-time singularity at the heart of the black hole, and then you have what is called event horizon. So this is the event horizon in this picture. You see, this is a space-time diagram. I think I should tell you that much. Space-time diagram. You see, here the time is going up. So this star is shrinking. This is the three-dimensional picture. The star is becoming smaller, but the star is evolving in time. So the entire star has collapsed here, to a single singularity, because no force of nature can resist whatever forces we know of. No force can resist, and so a black hole develops. Well, this is an artist impression, what a black hole looks like, and so on and so forth. But to summarize again, as I was telling you, I was talking in TIFR, to scientists. I gave a seminar, on black holes actually, and then eminent astronomers actually came up and told me, don't you have something better to do? Why are you talking, of this black holes? Do something, which is observed out there in the sky. But now, of course, black holes are everywhere, and in fact, if I do not talk of black holes, then I am asked, you see, that why your talk is not containing black holes. So, well, here you have in the title of my talk also black holes. Okay, but the point is, I told you this key scientific point. Of the whole thing. So, this also I told you. So now, the very important point, now I am coming to research frontiers. Okay, very quickly. A Oppenheimer and Schneider model was done in 1939, but the Einstein equations are very, very difficult to work with. Okay, and then people couldn't work out more models. That was a very idealized model. The whole star had, uniform density. It was totally spherical, no rotation. It's just like, drawing Gandhiji. You have seen that two-line picture. So, because you all have seen the picture, so you recognize that, this is, but, there are many details, right, to Gandhi or to any XYZ. So, I am just giving you a simile of how astronomers make a very simple picture. So that Oppenheimer-Schneider picture was like that. But then mathematicians couldn't work out any further models. So then what they did, they it was very convenient, make a hypothesis. ऐसे ही होता है. Okay, so that is what they do. Make a hypothesis. It is called cosmic censorship hypothesis. पूरा सेंसर पृथ्वी थिएटर में censorship, I don't know whether but the point is what it means is that the space-time singularity that I was showing you, which forms, you see, at the center of a black hole, that is this ultra high density region. So a black hole's key property is that, you see, this singularity is here, and the event horizon is totally covering it always. So you will never see this ultra dense region in the universe which is hiding at the center of a black hole. But they made a hypothesis. When I say they, it is the Roger Penrose and Stephen Hawking and others, that any massive star, and now I say any. Oh, Oppenheimer, Schneider, it was an idealized thing. But then real stars in the universe, they also make only black holes. This hypothesis was made in 1969. Then because they were very interested in explaining all these observations, so model building फिर शुरू हो गया कि every star goes to a black hole, and the question, very important question, will a generic star go? Generic means a real star in the sky. Will go the Oppenheimer-Schneider way only. Okay, so this is unanswered question. When real stars, inhomogeneous, in a real star density will be higher at the center, slowly decay, and then they have internal pressure forces. Okay, so this is an unanswered question, and that is where you see, I think, okay, let me now really summarize in a matter of 2 minutes. The current picture is something like this, to summarize for you. Average mass star goes to white dwarf. It will become red, sun will become red giant. There will be planetary nebula. You will have white dwarf. And if you have a heavy massive star, then it will be red supergiant, supernova will explode. Either you can have a neutron star, but if the star is beyond 10 solar masses, then you will have a black hole. But then here, this is subject to the censorship assumption. That's the key point. And now to really sort of before coming to, okay, there were so many applications made of black holes. We can talk about it a little later because I am told we have sufficient time for discussions actually. But more calculations were done in past 20 years. This is to come to research frontier. And then actually within the framework of general relativity, gravitational collapse was examined. The shrinking of a star is called gravitational collapse of the massive star. And it turned out that within Einstein's theory, you don't have necessarily black holes forming all the time. This is all within Einstein's theory, nothing funny. This is very important. You see, I am not bringing some ghost field. This is physicists are, this is another thing that they do. They bring in, phantom fields and, they achieve various things. Okay, but this is pure plain Einstein's theory of gravity, and it turned out when you did more calculations that actually there are stars which need not necessarily go into black holes. The ultra dense region at the center forming at the center of the star as predicted by the general theory of relativity, that becomes visible in violation to what was that censorship hypothesis. Calculations have been done, and to show you a diagram, sometimes the singularity is visible, sometimes it is hidden within the star. This is the black hole. This one could call a fireball, or sometimes a naked singularity. And then depending on the picture, or depending on what is inside the star, for example, for a star which is, you see, high at the density is high at the center and slowly decaying away from the center, then it could be a black hole or an exploding fireball. This is the current frontier. Now people are examining, there is a huge international debate actually going on this whole issue, that whether the final fate of a massive star is a black hole or a fireball. And then the famous guy also admitted that the fireballs could develop out of the sky. But then there were two people, P.C. Vaidya and A.K. Raichaudhuri. These people have contributed very profoundly. I again cannot go, unfortunately. If you want to ask a question, then you will give me an opportunity, then I will tell you. Okay, I am just prompting you. So, but they have made very profound contributions, leading to some of these developments. And then those who are more interested, you see, the Scientific American published a cover story. The interesting thing is, having come to Prithvi, I thought, I'll mention American, model and actor, Angela Shelton. She wrote several articles after reading this Scientific American article on her, blog on black holes and the massive stars and all that. So maybe Bollywood also can take some inspiration, start reading some science, okay, based on this. But okay, let me just conclude this. I'll come back if necessary. The question is this, and the developments are this, that either there could be black hole or there could be hypernova as a big blast of the star. And when you observe events like this, there's a major blast going on out there. Or I was showing you earlier, some active galactic nuclei and so on. It's still a mystery that what is the final fate of a massive star. But now we have progressed a lot in calculations, both numerically as well as analytically. By analytically, I mean doing the actual solutions of Einstein equations. And now lots of observations are also happening. So this major blast I was telling you, gamma ray bursts, you know, I mean, there's no theory at the moment existing. It's totally unknown phenomena. Scientists are, you know, trying to build models. So it's really research frontier. And then using Einstein theory, you like to model them, you know, using black holes, fireballs. So that's where we are, I guess. Yeah, man and the universe. And then now we can